In this lesson, we're going to look at the binomial probability distribution. It is a discrete probability distribution, and it has the following requirements. So first of all, we're performing a binomial experiment. That means that there's a fixed number of trials that we are going to perform, and I'll explain what a trial means in a second. In each trial, only two outcomes are possible. Those are usually considered success or failure. From one trial to the next, the probability of success does not change. In other words, the trials are independent. And then the random variable counts the number of successes that occur after the trials are completed. So you're going to do something a certain number of times, a fixed number of times, like you're going to roll a die, let's say 5 times, or you're going to toss a coin, let's say 7 times, or you're going to shoot an arrow at a target, let's say 6 times, or whatever it might be. You're going to do a fixed number of attempts at something, and then the trials have either success or failure. So when you're rolling a die, let's say you're trying to hit 6. So how many times do you actually hit a 6? 6 is success, and not getting a 6 is failure. And then from one trial to the next, the probability of success does not change. So the die does not remember what happened the previous time. It just restarts and you do it again. So if you have like, you're pulling marbles out of a hat, you'd have to put them back in, because otherwise the probabilities are going to change depending on what marble you picked. So that would not be a binomial. And then finally, the random variable counts the number of successes that occur. So if you're rolling your die, let's say 7 times, how many times do you get a 6? That's what the random variable counts. So the number of trials is called n, and the probability of success for each individual trial is called p. And then we have this notation now. So x, for example, could be my random variable. You could use capital Y or capital whatever. There's different capital letters are okay. We say x, and in this little tilde, we say x is distributed as, and then b stands for binomial, and then in parentheses we say n and p. So it'll actually say exactly how many trials and what the probability of trial of the success is for each trial. So x is distributed as a binomial with n trials and p probability of success for each trial. N and p are called the parameters of the random variable. So every binomial will have a different n and or a different p, and that's how you would determine how to do the problem. So x is distributed as a binomial with parameters n and p. So here's an example that I'm going to do in multiple ways to sort of describe different ways you can imagine this problem. So say we spin a square spinner with 3 blue sides and 1 yellow sides 3 times. So we're saying the square spinner has 4 sides, 3 of them are blue, 1 of them is yellow. So when we spin it once, there's a 3/4 probability of hitting blue and a 1/4 probability of hitting yellow. But we're going to do this experiment 3 times. We're going to have 3 trials of this spinning of the square spinner. So there's a fixed number of trials, in this case 3 of them. And we're going to count the number of times the spinner lands on blue. So we're counting out, the random variable counts out all the number of times that the spinner lands on blue, which could be 0 blue, 1 blue, 2 blue, or 3 blue. We don't care about the order. So we could describe this distribution as x is distributed as a binomial with n equals 3 and p equals 3/4. And again, that is read as distributed as, b stands for binomial, and then we say what n is, in this case 3 trials, so n equals 3, and what the probability of success for one trial is. We're trying to count the number of blue spinners, or times it hits blue. There are 3/4 probability for hitting blue, so p equals 3/4. So let me describe this in different ways. Let me start with the tree diagram. So this is the tree diagram that describes all the different outcomes that might occur, and I've put the probabilities on there: blue 3/4, yellow 1/4, and they don't change because the spinner doesn't remember. So if we follow the various paths that the probability distribution could take with the tree diagram, in order to get 3 blue, so if x is going to equal 3, since x counts the number of blue, we would have to go 3/4, 3/4, 3/4 for the probability. So 3/4 cubed will be the probability of getting exactly 3 blue. Now, in order to get x equal 2, in other words, 2 blue, that means you have 2 blues and 1 yellow, but it doesn't matter what order, so it could be blue, blue, yellow, or it could be blue, yellow, blue, or it could be yellow, blue, blue. So those are the 3 different ways you could do that Each of those ways has blue twice in some way, so 3/4 squared, and then yellow once in some way, so times 1/4. Similarly, to get exactly one blue, x equals 1, you have to have one blue and two yellow. So it could be blue, yellow, yellow, or it could be yellow, blue, yellow, or it could be yellow, yellow, blue. Again, 3/4 for getting exactly one blue times 1/4 squared for getting two yellows, and there's three different paths that have the same calculation, maybe in a different order, but there's three of those. And then finally for x equals 0, that's getting 0 blue out of the distribution. You'd have to have yellow, 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 so 1/4 cubed. So from the tree diagram, you can come up with the 4 different probabilities based on the number of blues that you want. Now, this is a rather tedious way to do the problem. Let me explain how you can really think about it a little differently and make your life a lot easier. So I'm going to take the example of getting 2 blue just to work out how that would work. So what you would do is you would say, I want to get the probability of x equals 2. So on my little thought bubble, I'd say, well, that means that I want to get 2 blues and a yellow, but I don't really care what order they are, so I'm going to figure all the quote-unquote words that involve 2 blues and a yellow. Well, that's 3 factorial divided by 2 factorial times 1 factorial. That's the different ways I could do that. 3 factorial over 2 factorial, 1 factorial, times the probability of just getting blue, blue, yellow, which would be 3/4 squared to get 2 blues, and then 1/4 to the first power to get 1 yellow. But you may recognize this. This is just 3 choose 2, or 3 choose 1 if you want to do it that way. So it's really 3 choose 2 times 3/4 squared times 1/4 to the first. And you can see this looks a lot like the binomial coefficients if A is 3/4 and B is 1/4, or B and Y are the two variables, and that's how you calculate the binomial probability for, in this case, x equals 2. Now, if I was just to expand 3/4 plus 1/4 cubed using the binomial a plus b cubed, this is what I would get. 3 choose 3, 3/4 cubed. 3 choose 2, 3/4 squared is 1/4 to the first. 3 choose 1, 3/4 to the 1, 1/4 squared, and then 3 choose 0, 1/4 cubed. And if I work out these coefficients, 3 choose 3 is 1, 3 choose 2 is 3, 3 choose 1 is 3, 3 choose 0 is 1, you recognize these 4 calculations as these 4 calculations that I did just by matching up all the paths that you could get. So expanding out this binomial gives you the 4 different probabilities. Now, here's another thing that's useful. For this to be a probability distribution, remember, all the probabilities have to be positive or 0, which would be okay. All these values are certainly positive, and also all the probabilities have to add up to 1. Well, here are all the probabilities, but wait a minute, they're equal to this. 3/4 plus 1/4 is 1, and 1 cubed is still 1. So this is indeed a probability distribution function. So here is sort of a quick summary of what we've discovered. If x is distributed as a binomial with parameters n and p, then the probability that x is equal to some value x, whatever it might be, lowercase x, is going to be n choose x times the probability of p raised to the x, and then times the probability, this is the failure rate raised to the n minus x, which is just your general old binomial expansion kind of formula, except we're using x here instead of r, and we're using p here for the a and the b part, the p and the 1 minus p. And of course, x can only take on the value 0, 1, 2, all the way up to n, because x counts the number of successes out of n trials as you are working out the probabilities. So here's a quick example. We want to expand 9/10 plus 1/10 raised to the 5th. Now this said expand, don't evaluate. Obviously, if you evaluate that, it's just 9/10 plus 1, that's 1. Raised to the 5th is just 1. So obviously, that's not what they want. So here I've expanded it, and instead of writing 5 choose 5, 5 choose 4, 5 choose 3, etc., I've just actually worked out what those coefficients are: 1, 5, 10, 10, 5, 1. And you can double check that if you need to. But otherwise, I've got 9/10 to the 5th, 9/10 to the 4th, 9/10 cubed, etc., all the way down, and 1/10, 1/10 squared, 1/10 cubed, 1 to the 4th, etc., to make this the a plus b raised to the 5th expansion. Now the question is, an archer has a 90% chance of hitting a target on each attempt. If 5 arrows are fired, find the probability of hitting exactly twice. So before I do that, I want to notice that I've discovered that I've got a binomial distribution here. So I can say x is distributed as a binomial. The parameters are, well, there were 5 arrows fired, so the number of trials was 5, so n equals 5. And we were counting the number of times we hit, so that's success is hitting. There was a 90% chance of hitting, so P equals, I could write 0.9 or I could write 9/10, because that will make it look a lot more like what we were doing over here. So x is a binomial with 5 trials and a probability of success each time of 9/10. Now the question is, what's the probability of hitting exactly twice? Well, there's a couple ways to do that. The first is to say I'm going to use the binomial expansion formula, the binomial probability formula to say the probability that x equals 2 is going to be, well, 5 choose 2 times the 9/10 squared times the 1/10 cubed. Another way to do it is to say, hey, wait a minute, I already know that this term right here is going to give me this exact same calculation. So this is the term, in fact, 5 choose 2 is just 10, and so I just need to work this out. So when I plug that into my calculator, I get 0.0081 as the probability of hitting exactly twice. Now the question is, what's the probability of hitting at most 3 times? So that means I'm asking for the probability that x is at most 3, so less than or equal to 3. Well, if x is less than or equal to 3, then there's lots of possible things that could happen. X could equal 0, x could equal 1, x could equal 2, or x could equal 3. Well, here they are. 0, 1, 2, or 3 successes. So these 4 terms have to be added up. Probability of getting 0, probability of getting 1, probability of getting 2, probability of getting 3 successes in my calculation. So to be really precise, I'm going to say this is the probability that x equals 0 plus the probability that x equals 1 plus the probability that x equals 2 plus the probability that x equals 3. And again, I'm going to use 1/10 to the 5th plus 5 times 9/10 times 1/10 to the 4th plus 10 times 9/10 squared times 1/10 cubed plus 10 times 9/10 cubed times 1/10 squared, because these were the corresponding terms that I had. I could have written this in reverse order, then I would have literally just been copying that in the same order, but I didn't, so it is what it is. And at this point, I just plug this into my calculator, and I get approximately equal to 0.0815. So the probability of hitting at most 3 times is 0.0815. Now you see both of these probabilities are kind of small, which makes sense because you have a 90% chance of hitting each time. So if you're going to attempt 5 attempts, getting only 3, it's not quite likely. Like you're going to hit a lot of these, so you expect your probability of hitting a small number of times to be kind of low. Now these are examples of using the binomial expansion formula, essentially, to calculate binomial probabilities. We are going to discover in the next lesson that if you have access to your calculator, you don't need to make it quite so complicated. The calculator can actually do these calculations for you a little quicker, but for right now, we are stuck having to do it manually. And that is the end of the lesson.